Okay, let's get started. Let's get started. In this video, we're going to do 6 problems. These 2 problems here, these 2, and these 2, and that's all we're going to do. But these 6 are a little more challenging when it comes to isolating the variable and simplifying what the variable is in radical form. Many of the problems we've done so far have been Pythagoras triples. Triples where they're all nice whole numbers, and that's nice as beginner and basic problems. But as we do this entire chapter dealing with simplifying radicals, it'd be nice to be able to leave our answers in radical form and be very sophisticated math students. So in this case, we have right triangles, and it's always helpful to recognize where the hypotenuse is. The hypotenuse is always going to be the opposite side to the 90-degree angle, or the right angle. So in this case, I can use Pythagoras. I can go 4 squared plus 6 squared equals x squared, because the hypotenuse is always going to go by itself. So in this case, we got 16 plus 36 equals x squared. And let's see, that's going to be 52 equals x squared. And so x equals the square root of 52. If you left your answer like this right now, it's not good enough, because the square root of 52 can be simplified. It turns out radical 4 times radical 13 is radical 52. So when we simplify this, this becomes 2 radical 13. Technically it's plus and minus, but in the context of this problem, we only have one solution here, and that's the positive one, because the length of x can't be negative. Let's try another one in here. This one's going to be a squared plus 60 squared equals 61 squared. Please ask yourself, do I know why the 61 is all by itself in here? That's because it's the hypotenuse. So in this case, what is 60 squared? I think that's 3600. And 61 squared, I'm not familiar with 61 squared. That's going to be 3721. So I move the 3600 on the other side, so a squared equals 121. So I square root both sides. Don't forget to do plus and minus, and it's plus and minus 11. But in the context of this problem, we're only using the positive root. This turns out to be a nice number here. So this is a Pythagoras triple on the right. The one on the left is not a Pythagoras triple. Let's do a few more. Let's take a look at this one here in blue on the left. So, we got some radicals, very intimidating, but Pythagoras' formula is still the same no matter what type of numbers here are represented on the sides. So I'm going to go radical 3 squared plus d squared, and that's radical 8 squared. You could be thinking, oh, I can simplify radical 8. Well, you can, but take notice, we're going to be squaring a radical. And whenever we square a radical, the radical goes away. So this is 3 plus d squared equals 8. So if I kept on going in here, I move the 3 onto the other side, d squared equals 5. I take the square root of both sides. So I can't simplify the square root of 5. Again, technically it's plus and minus 5, but in the context of this problem, d is just going to be radical 5 because it has to be positive. All right, so you can see solving for using Pythagoras' theorem in here could be a little more problematic if you're not comfortable with your radicals. Here's another example where we have some very intimidating radicals if you're not familiar with radicals. So in this case, we're going to have 2 radical 3, and we're going to square that. And then we're going to have 3 radical 5, and we're going to square that. Those are the 2 legs. And then what we want to find here is the hypotenuse. That goes all by itself. So when I square 2 radical 3, I'm actually squaring both of these. So when I square 2, it becomes 4, and when I square radical 3, it becomes 3, so that's going to be 12. In this case, when I square 3, it's going to be 9, and when I square radical 5, it's 5, so that's 45. So this looks like it's going to be 57 equals x squared, and when I take the square root of 57, square root of 57 is going to be stuck in the radical sign. for a very long time. This cannot be simplified. So that is the answer to this problem. We have x equals the square root of 57. Again, the intensity of the radicals is going up. Make sure you're comfortable with all the rules of how to simplify radicals. We got two more examples in here. So in this case, we have a little description here. Isosceles right triangles is a very specific type of right triangle where what? Where isosceles is referring to these legs. The legs are exactly the same. And so in this picture in here, the legs are exactly the same. And in geometry, we use these little tick marks. And if the tick marks are the same, these little double marks, if they're the same, that implies that the lengths of the sides are the same. In this case, we only used one tick mark, but since they're both exactly one tick mark, we know these two lengths are exactly the same. So sometimes in right triangles, we have the legs to be congruent. And that also implies what? That the base angles are then exactly 45. So this angle is 45 degrees, that angle is 45, this angle is 45, and that angle is 45. We didn't need to know that in the context of solving for these missing variables in here, but whenever we have a right isosceles triangle where the two legs are the same, this angle is going to be 45 and that angle is going to be 45. And if you take notice 90 degrees plus 45 plus 45, that equals 180 degrees, and that's a fact about all flat two-dimensional triangles. So how do I find x in here? Well, there's no variable in here, but if you think about it, if this one is being represented by x, this one should be represented by x because it's the same exact length. So now we have what? X squared plus x squared equals 100 squared. Keep in mind why did the 10 go by itself? Whoops, did I write 100 squared? Excuse me, it's 10 squared. The 10 goes by itself because it's the hypotenuse. So now, we haven't seen this before. How do we do this? Well, there's an invisible coefficient out in front here, that's a 1. There's an invisible coefficient out in here, that's a 1. And if you think about it, if I have one x squared and another x squared, I have two x squareds. So, again, you have to be comfortable when you simplify your radicals. In this case, we're adding radicals. The radicals, excuse me, not radicals. We're adding variables that have the same exact, we call these like terms from chapter 5 a long time ago. So make sure you're comfortable with chapter 5 and simplifying variables which are considered like. So if we keep on going here, to isolate x squared, I'm going to divide 2 by both sides. X squared equals 50. And then what do? I square root both sides. So this is x equals, well, 50 can be simplified here, radical 50. That turns into 25 and 2. Well, the square root of 25 is 5. So the answer here is 5 radical 2. So this leg would be 5 radical 2. This leg would be 5 radical 2. And we're done. That's all we had to find here was the length of that missing side in here. This was a leg, and it's the same for both of them. Let's try another one in here. The next one is, we just use a different variable. It's y. And let's see, how do we set this one up? Well, if this one is y, that implies that this leg has to be y as well because they're both the same. So I have y squared plus y squared equals 8 radical 2 squared. So in this case, I have 1 y squared and 1 y squared. That's 2y squared. And we saw this a few minutes ago. When we square this radical in here, we're actually squaring both numbers in here. Well, 8 squared is 64, and radical 2 squared is 2. So this is 2y squared equals 128. And so what do I do to both sides? To isolate y squared, I divide both sides by 2. I get y squared equals 64. If I square root both sides, this turns out to be a very nice number because the square root of 64 is a perfect square. So in this context, y is 8, and the other leg is 8 as well. Hopefully this has been helpful, and we'll see you on the next one.